The flight and nav data system comprises various systems which produce different types of flight and nav data outputs. An air data system uses pitot-static pressure for altitude, airspeed, and vertical speed calculations. The pressure data is output to two air data computers, which give inputs to the air data instruments on the flight deck. As we have seen, a single marker beacon antenna sends signals to each VHF nav receiver. The receivers output marker beacon data to EFIS. The PFDs show the marker indications. Which of the following data outputs does the VHF nav supply to EFIS? Please touch the highlighted area. That's right. The two VHF nav control panels are located on the glare shield. Each is supplied with radial or bearing information from its respective receiver. Each control panel has a frequency display. This has an upper and lower display field which shows tuned frequencies, radials, bearings or fail annunciations depending on the mode selected. A 4-position function selector which facilitates selection of the on, radial and bearing modes, a frequency transfer button which allows the standby and active frequencies to be swapped or direct tuning of the active frequency, and a 2-knob frequency selector. The outer knob tunes frequencies in steps of 1 MHz and the inner knob tunes in steps of 50 kHz. The frequency range that can be tuned is 108 MHz to 117.95 MHz. The control panel functions will be discussed in greater detail in the operations section. 2 DME systems are installed in the aircraft. Each DME system comprises an interrogator, an antenna, and a DME panel. The 2 DME systems are powered from different electrical buses. DME 1 receives power from DC bus 1 and DME 2 is powered from DC bus 2. The 2 DME panels are located on the captain's and first officer's instrument panels. VOR ILS and DME are usually co-located. Consequently, when a VOR station is tuned on the VHF nav control panel, the associated DME is automatically tuned at the same time. The audio identifier from the DME station is monitored via the appropriate selectors on the audio selector panel. Each DME interrogator transmits signals to the DME ground station via its associated antenna. The return signal from the ground stations is received by the same antenna. The 2 DME systems are each capable of scanning 2 channels simultaneously. The interrogators time the difference between the transmitted and received signals to calculate slant distance and ground speed to the DME station. During DME transmissions, a suppression pulse is sent to the ATC transponder. This is done to prevent interference between the ATC and DME systems, since they both use the same frequency band. The transponder sends a suppression pulse to the DME during its own transmissions. The DME system outputs distance information to EFIS. The distance in nautical miles is displayed on the navigation display. The DME interrogators also output data to their DME panels. Each panel normally displays distance in nautical miles and the ground speed in knots. Note, the ground speed is only accurate when the aircraft is flying directly to or from the DME station. In addition to the distance and ground speed values shown in the DME display, the DME panel provides other mode selections. These are a time to station button, a hold button which when pushed holds the last tuned DME frequency. This frequency then remains active even if other frequencies are tuned on the VHF nav receiver. And finally a nav button which exchanges nav 1 for nav 2 or vice versa. The DME system has a memory function which will hold on to a station for up to 12 seconds if its transmission signal is lost. To test your understanding of this section, you will now be presented with several multiple-choice questions. Which of the answers describes how DME ground stations are tuned? That's right. During DME transmissions, a suppression pulse is sent to which system to prevent interference? Please touch the highlighted area. Yes. 2 automatic direction finding systems are installed on the aircraft. These are designated ADF-1 and ADF-2. Each ADF system consists of an antenna, a receiver, and a control panel. The electrical power sources for the ADF systems are emergency DC bus 1 for ADF-1 and DC bus 2 for ADF-2. The function of each ADF is to provide the bearing to and the identification of selected non-directional beacon stations. The radio signals from the NDB are received by a combined loop-sense antenna on the underside of the fuselage. There are 2 antennas, one for each ADF system. The loop-sense antenna is direction sensitive. The receiving antenna outputs the NDB signal to its corresponding ADF receiver. The receiver sends the NDB identification signal to the audio integrating system. Audio signals from the NDB station can be monitored by the crew via the audio selector panel on the pedestal. In addition to outputting the NDB audio signals, the ADF receivers also calculate either the relative bearing of the aircraft to the NDB station or the magnetic bearing. Both AHARs provide heading reference data to their respective ADF systems. This data is used by the ADFs to calculate the magnetic bearing of the NDB station. What type of antenna does the ADF system use for direction finding? That's right. The ADF receivers output relative bearing information to EFIS. The navigation display shows the radio navigation aids selected at the EFIS control panel, and 2 bearing pointers indicate the relative bearing of the selected radio navigation sources. The blue pointer orientates to the ADF-1 station, and the green pointer orientates to ADF-2. Both ADFs also send relative bearing information to the RMIs. Each ADF system orientates a particular pointer on the RMIs. The signal from ADF-1 controls the single pointer on each RMI, and the signal from ADF-2 controls the double pointer on either or both RMIs. Each RMI has an associated set of pointer selectors located beside it. The pointer selectors allow selection of ADF-1 or ADF-2 or VOR1 or VOR2 as the signal source for the RMI pointers. Each ADF receiver outputs relative and magnetic bearing data to its respective control panel. The control panels in turn provide mode and frequency selection to their ADF receivers. The ADF control panels are located on the rear pedestal. Each ADF control panel has a frequency display window. The display window has two data fields, an upper and a lower one. These data fields can be occupied by frequencies, as shown here, bearings, fail annunciations, or test displays according to the mode of operation selected. A frequency transfer button allows active and standby frequencies to be swapped or enables direct tuning of the active frequency. The Tuning Select button alternates between tuning in steps of 1 kHz or 0.5 kHz. It also displays relative bearing during the test procedure. A 6-position function selector for choosing different modes of operation, and finally a 2-knob frequency selector. The frequency selector allows tuning within a frequency range of 190.00 kHz to 1860.00 kHz. To test your understanding of this section, indicate the location of the ADF control panels on the flight deck graphic. Please touch the two ADF control panels are located on the rear pedestal. What is the frequency range of the ADF receivers? That's right. The function selector on the nav control panel allows various mode selections to be made. In the off position shown here, the frequency display is blank. The VHF nav system is made operative by selecting any of the 3 active modes on the function selector. Select the on mode by operating the function selector. In the on position, the frequency display shows the last tuned frequencies. The upper display field shows the active frequency, and the lower field displays the standby frequency. The number shown on the left side of the frequency display window indicates the nav system being used, in this case nav 1. Select radial mode on the function selector. In radial mode, the radial from the tuned VOR station is displayed in the lower display field. The active frequency remains in the top display field. If an ILS has been tuned on the nav receiver, the lower display field will show a localizer indication when radial mode is selected. Select the bearing mode on the control panel. When bearing mode is selected, the lower display field shows the magnetic bearing of the tuned VOR station. If bearing mode is selected and an ILS is tuned, LOC appears in the lower display field. If either on, radial or bearing is selected on the control panel and a VOR station is selected, the ND bearing pointers will show the magnetic bearing to that station. If the VHF nav receiver is tuned to an ILS indication, glide slope deviation pointer and scale appear on the ND. Glide slope and localizer deviation pointers and scale will also appear on the PFD if an ILS is tuned and selected. The bearing pointers on the RMIs will show the magnetic bearing to the VOR stations, if these stations have been selected as the nav sources for the RMI. New VOR or ILS frequencies are tuned via the frequency selector knobs. As we have seen, the outer knob tunes in steps of 1 MHz and the inner knob tunes frequencies in steps of 50 kHz. By using the correct frequency selection knob, tune the standby frequency to 110.60 MHz. The standby and active frequencies can be swapped over by pressing the frequency transfer button. Now use the frequency transfer button to swap the standby and active. That's right. If the frequency transfer button is pressed for 2 seconds, it is possible to tune the active frequency directly. Assume that a new active frequency of 116.30 is required. Tune the new frequency by first rotating the outer frequency selector knob. Yes. When the active frequency has been tuned, the standby frequency is restored by once again pressing the frequency transfer button for 2 seconds. Pressing the frequency transfer button for 7 seconds or more resets the active frequency to 108.00 MHz. The VHF nav systems are self-monitoring and generate failure indications. A fail message in the lower display field indicates a complete failure of that nav system. Dashes in the lower frequency display window with radial or bearing mode selected are indicative of no signals being received from the tuned VOR. As we have seen in a previous section, the VHF nav receivers auto-tune the DME station whenever a VOR ILS station is tuned. The DME transceiver transmits to and receives signals from the DME ground station. Typically, the DME indicator shows the distance to the DME station and the ground speed. The indicator can also show the time to station value. Press the appropriate control on the DME panel to display the time to station. Pressing the TTS button displays the time to station based on the distance and ground speed. Pressing the TTS button again restores the ground speed value. Restore the ground speed indication on the DME panel. Pressing the hold button disconnects the DME from the VHF nav frequency control. The currently selected nav DME source is then held regardless of subsequent selections. Select the hold mode on the DME panel. In hold mode, the ND loses the DME distance and ground speed information. Hold mode is cancelled by touching the hold button again. Pressing the hold button cancels the hold condition and restores the ground speed on the DME panel and both ground speed and distance on the ND. Finally, the nav button on the DME panel is used to exchange the VHF nav sources. Change the VHF nav source for the DME by selecting NAV2. Each DME panel can use either NAV1 or NAV2 as the source for DME displays. There are 2 ADF control panels, one for ADF1 and one for ADF2. Both panels function in exactly the same way. The system starts to operate as soon as the function selector is rotated from the off position to any one of the operational modes. Activate the unit by selecting the antenna position with the function selector. In the antenna mode, The display window shows the active and standby frequencies that were last tuned on the unit. On the left of the display window are annunciators indicating the active frequency and the ADF system being used, in this case ADF1. With antenna selected on the unit, the ADF receiver only uses the sense antenna. Consequently, no directional information is received, and the RMI and ND pointers park at the 3 o'clock position. This mode is used for tuning NDB stations since it produces the best audio reception for station identification. Select the ADF position on the control panel. The ADF position provides a direction-finding mode. In ADF mode, the bearing pointers on the RMIs and NDs orientate towards the selected NDB stations. Select the bearing mode on the ADF control panel. The bearing position is another direction-finding mode. The lower display shows the magnetic bearing to the active NDB station. Select the BFO mode on the ADF control. BFO mode is similar to ADF mode in that it provides relative bearing outputs to the bearing pointers. The BFO mode adds a 1000 Hz tone to the audio output. This allows identification of those stations transmitting a carrier without audio modulation. The last position that can be selected on the function selector is Test Mode. Select Test Mode on the control panel. Test Mode initiates an ADF system test. When selected, a pause message appears in the lower field display. After a moment, the pause message disappears and is replaced by the letter L and a number. If the number is greater than 10, the ADF system has successfully passed the test. The Tuning Select button is used during test mode to provide additional test information. Press the Tuning Select button as part of the system test procedure. Please touch the highlighted area. If the Tuning Select button is pressed during test mode, the relative bearing of the active station is displayed. During the ADF system test, the bearing pointers on the RMIs and NDs park at the 90-degree position if the ADFs have been selected as the radio nav source. A new frequency is tuned using the frequency selector. The frequency selector consists of two knobs, an outer knob which tunes the frequency in steps of 100 kHz, and an inner knob which tunes frequencies in steps of 1 kHz. Pressing the Tuning Select button allows tuning to be carried out in smaller frequency steps. Select the control for incrementing the frequency in smaller steps. Note that a decimal point and extra digit appear in the standby frequency display. The inner knob of the frequency selector now changes the frequency in steps of 0.5 kHz. Pressing the Tuning Select button again restores the whole number frequency step for tuning. The inner knob of the frequency selector once again changes the frequency in 1 kHz steps. Either the standby or active frequency can be tuned using the frequency selector. Tune the standby frequency to a new value of 815 kHz. Rotating the outer knob changes the standby frequency in steps of 100 kHz. The frequency transfer button, if pressed momentarily, exchanges the standby and active frequencies. Exchange the standby and active frequencies. Please touch the highlighted area. The standby frequency has now become the active frequency. By pressing the frequency transfer button for 2 seconds, it is possible to tune the active frequency directly. Note that the standby frequency disappears. Now, tune the active frequency to a new value of 835 kHz. Please touch the high. When the active frequency has been tuned, the standby frequency can be restored by pressing the frequency transfer button for another 2 seconds. Tuning of the standby frequency is once again available. The ADF system is inoperative if a fail message is displayed in the frequency display window. If no signals are received from the tuned station, dashes appear in the lower display field. The F-50 is equipped with 2 self-monitoring VHF nav systems. Their function is to process VOR-ILS ground station signals. The VHF nav systems also receive marker beacon signals. 2 control panels located on the glare shield provide mode selection and frequency selection. The frequency range of the units is 108 to 117.95 MHz. A frequency display window on each control panel shows frequencies, bearings or radials depending on the mode selected. The VHF nav systems output data to EFIS. This data provides visual displays for glide slope, localizer, course deviation, radials and magnetic bearings to tuned stations. Marker beacons are also shown. The bearing pointers of the RMIs receive outputs from the VHF nav systems. VOR and ILS information is also supplied to the automatic flight control system. Two dual-range DME systems provide slant distance and ground speed information. DME ground stations are automatically tuned when a VOR-ILS station is selected via the VHF nav control panels. The DME systems output data to DME panels located on the captain's and first officer's instrument panels. The DME panels show distance, ground speed, hold frequency or time to station depending on the mode selected. DME data is also output to the navigation displays. 2 ADF systems are also installed on the aircraft. Their function is to receive and process signals from low-frequency NDB stations. 2 ADF control panels are located on the rear pedestal. Each ADF panel has a frequency display window which shows tuned frequencies, magnetic or relative bearings, or test indications depending on the mode selected. A 6-position function selector allows different modes to be selected. A frequency selector provides frequency tuning in the range 190.00 to 1860 kHz. ADF systems provide NDB bearing information to the navigation displays in full and arc modes. ADF bearing information is also sent to the RMIs. The F-50 is equipped with one radio altimeter. The radio altimeter is a transceiver and is located beneath the rear cabin floor. Located close to the radio altimeter on the underside of the aircraft is the dual antenna used by the radio altimeter system. The forward antenna is used for transmitting the radio altimeter signal, whilst the rear antenna is used for reception. During radio altimeter operation, the transceiver outputs signals continuously from the forward antenna. These signals are directed down towards the ground. The signals are reflected back from the ground and received by the rear antenna of the radio altimeter system. There is a delay between the transmission and reception of the signal, and this delay increases with aircraft altitude. The radio altimeter system times the delay between the transmission and reception of the signals and uses this data to calculate the altitude. The operating range of the radio altimeter is from 0 to 2,500 feet. Operation of the system is automatic. There are no flight deck controls. The altitude data calculated by the radio altimeter is output to various aircraft systems. These are the flight data recorder, the automatic flight control system, the ground proximity warning system, the integrated alerting system, and the electronic flight instrument system. At altitudes between 0 and 2,500 feet, the altitude calculated by the radio altimeter is shown on the primary flight displays. The PFD indications will be discussed in greater detail in a later module. To conclude this lesson on the radio altimeter, attempt the following questions. Which of the following does not receive data from the radio altimeter? Please touch the highlight. That's right. Assume that the aircraft is flying at 2,700 feet. What radio altimeter value would you expect to see on the PFD? That's right. Since the radio altimeter is only operational when the aircraft is between 0 and 2,500 feet, no indications would appear on the PFD at heights greater than 2,500 feet. The flight and nav data system includes 4 separate subsystems: the air data, AHARS, radio nav, and radio altimeter systems. The air data system uses pitot-static pressure derived from 4 pitot-static heads. The pressure data is supplied to 2 air data computers, which in turn supply other aircraft systems with speed and altitude data. Pitot-static pressure information is also supplied to the standby instruments on the flight deck. The 2 attitude and heading reference systems use accelerometers and rate gyros to produce pitch, roll, yaw, rate of turn, and acceleration data. AHARS also supplies heading reference data by means of magnetic sensor units and directional gyros. AHARS outputs attitude and heading reference data to various aircraft systems, including EFIS, AFCS, and the radio nav system. The radio navigation system is made up of a VHF nav, a DME, and an ADS system. 2 VHF nav systems are installed which provide VOR, ILS, and marker beacon information. This data is output to EFIS, the RMIs, and to the VHF nav control panels. The 2 DME systems provide ground speed, distance, and time to station data. This information is output to EFIS and to the DME control panels. Two ADS systems provide navigation data from low-frequency NDB ground stations. The bearing data from the ADS is output to EFIS, RMIs, and the ADF control panels. One radio altimeter system is installed. This provides accurate altitude information within its operating range of 0 to 2,500 feet. Altitude data from the radio altimeter is output to EFIS, the flight data recorder, the automatic flight control system, the ground proximity warning system, and the integrated alerting system.